Hello and welcome to this festive tech calendar session. Today the topic is recursion at Christmas with festive mazes in C#. My name is John Kilmister and I've been a software engineer now for many years. You can find me on Twitter at John Kilmister. I also have a blog at blueboxes.co.uk where you can find articles on C# and Azure. In today's session we're going to have a look at all things mazes. We'll start off by talking about different maze algorithms before taking a deeper look at the Backtracker algorithm. We'll then look at how we implement this in C#, save it to a JPEG, before finally looking at how we can take our square mazes and turn them into festive shapes such as this tree or snowman. Before we get too far though, let's have a quick recap on the differences between a labyrinth and a maze. Well, a labyrinth, as we can see on the left hand side here, has a single route through. There are no alternate paths, no dead ends, just one single continuous route. A maze, on the other hand, like this on the right, has many dead ends, has lots of channels, and is much more complex. And that's what we're going to focus on today, generating these mazes randomly in C#. Now, like many problems in software engineering, there's more than one way to complete them. And maze algorithms are no different. There are 11 different ways, or 11 different algorithms, should we say, to create mazes. And why do we have all these different ways? Well, although they all generate a perfect maze, in which you can navigate between any 2 points, the actual implementation determines how the maze looks. We can see here on the left hand side we've got a randomized prims algorithm. On the right we have a recursive division algorithm. We don't need to go into the detail of these at this point, but you can quickly see that they generate two very different maze structures. And between all of the maze algorithms there are differences. Different lengths in the corridors, different numbers of dead ends, different lengths of those dead ends. And many of the maze algorithms will also have biases. For example, this one here has a horizontal bias, so you can see that most of the corridors are along a horizontal axis. Well, today we're going to take a look at the Backtracker algorithm. This is one of the more common algorithms and has a good balance between the complexity to implement and the number of dead ends and the length of the corridors. So how does it work? Well, the first step is selecting a starting cell. You can actually start at any cell, but for simplicity we're just going to start at 0, 0. The next step is to choose an available neighbour at random. So in this case we can move to either 0, 1 or 1, 0. And when we move to this new cell, we'll break the wall in between them. Then we'll repeat, and we will keep repeating, breaking the cell walls and moving to the next available neighbour randomly. And as we continue on, we forge a path all the way through until we get to a point where we no longer have any neighbours that we can visit. At this point, we can start backtracking and we go back along the route that we came. We first look at the next cell that we've been to, and if that doesn't have any neighbours, we go back again until eventually we get to a point in which we do have unvisited neighbouring cells. Then we forge a path through these, and once that's complete we go backwards again. Once all the cells are visited, we'll eventually find ourselves right back at the starting square, and we know that the maze will be complete. The very final stage is to carve an entrance and an exit to our maze. Now, any of the exterior walls could have an entrance or exit. You can get from any point to any other point in the maze. We'll just pick 0, 0 and 0, 2. When we see this on a larger scale, it makes a bit more sense. You can see here we're randomly carving out a path, and when we get to the end we navigate back until we find another neighbour that we can go to, and we start carving a path in that direction. And once that gets to a dead end, no neighbouring cells that we haven't visited, we back out and we do it again. And with this approach, we can quickly create a new maze. This animation is actually made up of 1600 different steps and takes about a minute or so to run. If we were to take out the animation, it would only take a few seconds to run. So that's the theory behind the Backtracker algorithm. But how do we go and implement this in C#? Well, the first thing we need to think about is our data structures. A maze itself is a graph. We have one node, you can navigate to another node, that navigates to another adjacent node. But as we're looking at square mazes here, we can simplify this down into a two-dimensional structure. And in C# we've got two main ways of representing this. We can either start with a jagged array or an array of arrays. At first, we declare our outer array, and this is going to represent each row in the grid. And then against each row, we'll have a new array, and this will actually have the entries for each of the cells and represent the columns. To access it, we can just use the indexes of row followed by column, and then we can either set or read the values. To get the height of the grid, we just have to get the length of the outer array. And to get the width, we can get the length of any of the child arrays. Alternatively, and more efficiently, we can use a multi-dimension array. And in this case, we just require a two-dimensional array. We can initialize it in a single command, and accessing the elements is relatively similar. Although in this case, we pass both the row and the column into the indexer. To get the height and the width is slightly more complicated. We can't just ask for the length because we might have many dimensions. So we have to actually use the getLength method, passing either 0 for our height or 1 for our width. But overall, the multidimensional array in .NET Core and .NET 5 and 6 is a much more efficient way than using a jagged array. There's less steps involved when it gets converted to IL. So we have a way now of storing our data, or a shape for it, but what do we actually want to put into each of these array entries? Well, the Python library mazelib uses this approach. It actually represents the walls as separate entries in the array. So we can see here that columns 0, 2, 4 and 6 are all walls, as are rows 0, 2, 4 and 6. And the corridors start at 1, 1. Now if we want to break into the adjacent cell, we then have to just knock a hole through to 1, 2. So this means that we can quite simply have our array as a Boolean array. Just has it got a wall or has it not got a wall? But it does make things more complicated later when we start to try and draw these out. The alternative approach is to store all of the walls in each entry in the array. With this approach, we do have to remove two walls when we want to move from one cell to another. We have to remove the eastern wall of the first cell and the western wall of the second cell to allow us to move across. Now, in the previous example, we were able to represent it all with a Boolean in each field. But now we're trying to store 4 different values for the 4 different walls in each cell. So how do we do that? We can represent multiple values into a single field using a flags enum. We don't have a lot of time to go into the details of flags enums now. However, by marking your enum up with flags and using bitwise operators, we can combine multiple values into a single one. So in our initial set, we're taking all 4 directions, east, south, west and north, using a bitwise operator to combine them into a single value and putting them into this single array entry. When we want to break through from one cell to another, we can just remove the wall. Firstly removing the east wall and then on the adjacent cell, removing the west wall. The flag enum also has a helper method called hasFlag, and this can be really useful. So when we come to draw the maze later on and we want to decide if to draw the northern wall, then we can just ask it, has it got that flag? And it will just return a Boolean. So that's what data we're going to. So that's what data we're going to store. But let's now look at the actual algorithm and the implementation. And then for this, we're going to use a C# stack collection. This is the opposite of a queue, if you've used it before, and works on LIFO, last in, first out. If you've not used either before, don't worry. As we go through this, it will make a bit more sense. So at the start of this, we create a stack collection. And this is going to be used to track all the cells that we visit. To start with, we push in the first maze point, 0, 0. And that's going to be our starting point. And the core of this implementation is to loop while we've got items in our tracking collection. On the first line, we take a peek at the list. So, peek will return the first item in that stack, but without actually removing it. We then look for all adjacent cells that we can move to. In this case, we'll only have one. If we do have one, which we do in this case, we'll then break through the wall and start tracking the next cell. As you can see, our track stack collection now has 2 entries in it. So when we go back around the loop, we meet our condition and we come back in. And we grab the top item out of that stack again, but without removing it. And we look for the next adjacent cell. We do have one, so we break through the wall and we start tracking again. And we go through the loop again and we find ourselves taking the peek at the stack, and we've got cell 2, 0. Now, the next bit, getting all the neighbours. In this case, we don't have any neighbours that we haven't visited before. So, we fall through to here. And at this point, we start backtracking. And we do that by popping the top item off the list. So now we go back around again. And we still have more items in our list to process. But again, we take the top item out to peek. And from that, we then look at all neighbouring cells that we haven't visited. But in this case, again, we don't have any. So we'll pop the top item off the list. And again, we'll go around and grab the next one. Nothing to visit. And therefore, it pops off the list. Before finally realising that we don't have anything and the maze is now complete. In this simple example, we were just carving a straight line down. However, if you've got a full grid, it will actually create your entire maze for you. But this isn't the only way to create a maze using the Backtracker algorithm. We can actually use recursion. So we can use recursion in lots of different applications. In this application, we're drawing a folder node. And the method that draws the folder node will go on to draw a folder icon. But then it will loop through and draw all of its children. And where recursion comes in is that we'll actually do that by calling the draw folder method again. So recursion is when we've got one method that calls itself. And in this case, it will then draw out the child node and all its children until we get to a point where there are no more children, and it will then go back up the call stack, filling in the remaining children of the parent and then the remaining children of that parent until we've drawn the entire tree. And we can follow a similar process when looking at the Backtracker algorithm. So this is the implementation of the recursive backtracker. It looks quite different than the previous implementation, and we'll go through it line by line to explain how it works. But the underlying algorithm and the concept of a backtracker is exactly the same. So we create a method In this case, I've called it move to. And this is the method we're going to call each time we want to navigate between one cell to another. We start off by calling it with 0, 0, which is our initial cell that we want to start in. That takes us into the method. And the first thing we do is we get all of the directions. So north, south, east and west. And we'll randomize them so that each time we're heading in different random directions. We take the first one in that list and say we use south as an example. We'll then calculate what the cell that we'll be going to would be. So in this case, we'd be calculating that it would be 0, 1. We check that that is available, which a southerly cell of 1, 0 would be. So like previously, we then break our walls through. Now the key difference here is that we don't add that to a tracking list and loop again. We actually use the call stack to do the tracking. So we call this same method again, move to, but this time we're putting in the new row and new column. So we've now moved to that new cell. And again we get all 4 directions and we pick one of them. If we were to have north as our first direction, we'd calculate that cell. But this time north is not available. We've already visited that cell. So we skip over that. And we go around again. And we'll keep looping until we do have an available cell. So our southerly cell is available. So once again, we break through and then we move to that cell by calling the same method again. So we're now calling the method with the parameters to 0. Now this time we get all 4 directions. We're actually going to loop through this 4 times because none of those 4 directions are available, as every cell has been visited in our short list. So what happens here is at the end of the 4th iteration and the 4th direction, we just return the grid. Now that's going to return it to its previous location, which was here. And from here, the parameters that we'll have in the values row and col will be 1, 0. We'll then continue looping for all the directions that we didn't previously go through when we were in this cell. There aren't any available that we haven't visited, so that will eventually return the grid. And again, we'll end up returning back to the move to call that we had here, but with the parameters 0, 0. And we'll iterate through the directions we haven't visited, seeing if we can navigate anywhere else, which in this case we can't. So finally, we return the grid to the outermost call here. And the grid is complete and we have a full maze. So this is just an alternative way of generating a maze using the same Backtracker algorithm. However, it is using recursion and the call stack to keep track of where we've been, rather than using a C# stack. So we now have a maze in memory, but we do need to save this out so we can actually visualize it. Now, as we're doing this all in C#, we're going to continue to do this with GDI+. However, you could use the same techniques to draw out an SVG file or other file format. What we're looking at doing is generating a maze that has wide corridors and narrow walls. So to do this, we'll create a simple save to JPEG method. This will take the path that we're going to save to, along with the grid that we've pre-populated with our maze. The first bit is to create a new bitmap. The width and the height are relatively easy to work out. We know the width of the grid and the height of the grid. We just need to multiply that by the size of each of the cells that we wish to draw out. The next step is to create a graphics object, and this is really just a canvas which we can use all of the GDI+ methods on to draw. And the first method is .clear, and this gives us a solid background color. If we don't do this, we just get a black background. And the final step would be to take this graphics object and to draw it back to the bitmap and save it out as a JPEG. But if we were just to leave it at this, all we'd be left with is a solid grey box. So how do we actually draw the maze? Loop through each of the rows and each of the columns and call our draw cell method. We can decide if to draw each of the walls. We can ask, is there a northern wall? And if so, draw a line across the top. Is there a southern wall? If so, draw a line across the bottom. Is there an eastern wall? If so, draw one on the right. Otherwise, if there's a western wall, draw one on the left. So this has flags method that's part of a flags enum, allows us to quickly decide which walls to draw. As I said, this is in GDI+, but you could equally be rendering out nodes in an SVG or other methods. So that draws us a nice square maze. But what if we want to create a shaped maze in the shape of a Christmas tree or a snowman, like we saw at the beginning of the presentation? Well, for that, we can use a few extra techniques. You may have spotted right at the beginning in the flags enum an extra value called none, which we haven't used up until this point. But by using this, we can mark individual array entries not to render anything at all. So if we take a snowman picture here and we go through each pixel and we make each pixel represented to one cell in our maze grid. And then for every transparent pixel, we mark it as none. And then for every non-transparent pixel, we mark it with the 4 walls to give us the start of our maze. Then we can actually carve a path through all of the cells that are available. Remembering, we only will visit available cells, and the way we identify an available cell is that it has 4 walls. So how do we load that in? Well, we load the bitmap object and we create a grid that is the same size as the bitmap is in pixels. We then loop through each row and each column of pixels, grabbing it. If it's a transparent pixel, then we set the direction in the cells to none. Otherwise, we set them to all directions, with all directions being a constant that stores each of the 4 enum values. So if we render the maze at this point, it looks like this, because we just have an array that either has cells that contain none or contain all 4 walls. Now, if we start our maze algorithm trying to generate at 0, 0, it's not going to work because it's only going to be looking to move to an adjacent cell that has all 4 walls. And as we can see in the top left-hand corner at 0, 0, that isn't the case. So we have to make sure we start our maze algorithm now right in the center of our picture. But once that's done, we can start our maze algorithm carving its paths out, which then leads to a maze that looks like this. The final step is to quickly add an entrance and exit to our maze, which we can do by finding any of the exterior cells. What if we want to add a bit more colour though? This roughly looks like a snowman, but it would look so much more like a snowman if we added some colour. Well, when we go through the cells and work out if they're transparent or not, we could save off the colour and its position. Then when we start drawing the maze, we can decide either to draw the lines in that colour, as you can see on the left hand side, or we can set a background colour for that cell, as you can see on the right hand side. So there's lots of possibilities that you can play around with once you get access to the individual pixels. If you want to have a look at this in full, you can see all of the code on my GitHub at blueboxes/image to maze. You can also just run it, give it an image, and you'll be generated an image maze. What if you've been inspired by all of this today and you want to take this a bit further? Well, there's loads more things that you can play around with mazes. You can create mazes that aren't square. You can use circular mazes, for example. Or you could change the cell shape, hexagons, triangles, various other shapes. Alternatively, you can use the data to actually create a tile maze. These are actually SVG tiles that have all been put together based on the data in the array. And finally, you could start adding in tunnels and bridges into your maze to make it even more complex. That just leaves me to say thank you for watching, and be sure to check out the other videos at festivetechcalendar.com.